Hello, everyone. I think it's 2 o'clock. Let's go to start. So, welcome to this event. It's a pleasure to see so many people attending what is a quite interesting topic today. So, today we have Youcheng. Youcheng is a lecturer in the software system security group in the computer science department. And I got to meet Youcheng and collaborate with Youcheng for the past couple of years. And as an AI safety researcher, every time I have to introduce Youcheng or even just read his bio, I'm thoroughly impressed. So Youcheng did his PhD at one of the top universities in Italy, a school of Fontana, and then for a postdoc to Oxford, and then to a lectureship in Belfast, and he finally joined us in Manchester, which is knowledgeable. And he worked on a quite impressive roster of projects. He was funded by Google, by the Ethereum Foundation, and several defense projects from the UK. And he is an expert primarily in software safety and security. And he led some project on software security, but basically, of course, as they say, AI is eating software. So of course, software security now is becoming also AI security. And he had 2 projects, including our European projects, on the safety of cyber physical systems. And today he's gonna tell us something about intellectual property protection of deep learning systems. So without further ado, I'll open the floor for you, Chance.
Thank you, Adam. Thank you very much. Thank you, everybody, for joining. So today we are going to talk about the copyright protection problem for deep learning models. My primary goal of this presentation is to bring this problem to the audience and to introduce the challenges and also opportunities along with it. I'm also more than glad to hear your opinions and feedback. As a computer scientist, I had to admit the meanings, the interpretations of intellectual property or copyright in this work, they are based on common sense. Their exact legal meanings should be subject to experts on laws. First of all, it should be very clear nowadays, AI models, deep learning models, they are very valuable assets. Nowadays, I mean, the most useful AI models could easily cost millions of dollars, if not more. They are very expensive. Big companies, actually, for the most sophisticated models, I mean, it's beyond the resource availability of many institutes. So big companies, they invest a lot of resources, energies, and human efforts on developing the most popular models. On the other hand, I mean, we have such expensive, such sophisticated models. On the other hand, people, hackers, I mean, or interested people, they could rather easily replicate these very complex models by using the budget of several hundreds. Of course, I mean, such replicated model, such model is extracted from the original complex one. They may not perform as well as the original one. But I mean, they are not bad. And the biggest thing is, I mean, you only spend very little money and you can get a model that has similar performance as the original, very complex one, by only, for example, querying the publicly available APIs of the original model. This gives us sense that for the owners, for the companies who own these complex, expensive models, they have the incentive, there is the incentive for them to protect their models, their AI models, their assets from unauthorized replication or unauthorized copy. There is another group of numbers. So if we look at our phones, there are many computer vision related apps, CVI. According to a survey study, the majority of such CVX in Android phone, they share very similar structure of parameters for the underlying AI models that are used. In fact, most of them are identical, and it's a model called MobileNet. I mean, that is a very popular image model that are tailored for mobile devices and expandable. Actually, this could be generalized. This fact could be generalized. If you look at the AI models developed nowadays, if you look a bit closer, I mean, they all look very similar to each other. And I mean, many of us, I mean, may think, okay, so what? I mean, they are similar from each other because once there are some popular models by some research group like VGG, like others, so they are published. And the people fine-tune, people redevelop their own models based on this successful one. This is what has been done. This is what has been done for many years for machine learning, for deep learning. So I mean, why there is a problem? There are huge problems from security perspective. I'm not going to argue with you on this. The thing is since ChatGPT, since there is ChatGPT, it becomes easier for me to convince people that I mean, there is a problem. There is a problem for this pattern, for this scheme. So I mean, ChatGPT, I mean, it's so popular, but it's ChatGPT 3.5, so it's so popular. But actually, it's not that long time ago. I mean, earlier this year or later last year, there was the ChatGPT 3.5, and suddenly everybody in the world, everywhere is talking about generative AI and large language models. And of course, there are so many companies. They also publish their own large language models as the competitor of ChatGPT. So there is such a company. And I will not, because I was told this is recorded, so I will not say the name of this company. And so, I mean, this company, it has this, I mean, large language model, competitor of ChatGPT, as tons of hundreds of other models. So, okay, so I mean, it's similar. It works similar to ChatGPT, and it also provided one additional very popular functionality. That is, okay, by typing the text, it could also generate the figure, generate the image for you, given the description. So some netizens, some people ask the model from the company to generate an image of Kung Po chicken. What is Kung Po chicken? So if you go to, there are many good Chinese restaurants in Manchester. There are also many bad ones. So if you go to the bad ones, they are also good ones. You should know that. So if you go to almost every Chinese restaurant, there is a very famous dish that is called Kung Po chicken. And if you order it, you will see it's different from this image generated. So I mean, it's a proper dish. It's a proper dish. You may or may not like it, but it's not. It's different from this Kung Po chicken generated by this AI product, by this model. I mean, what is Kung Po chicken? So there is peanuts, there is chicken. Okay, there is peanuts, there is chicken, but this is not the dish that you see. Anyway, so at first people feel this is really funny. This is really funny. So I mean, netizens are very optimistic. But later, I mean, as people found more and more such examples, some people did realize that, okay, it seems that this company's AI model, it might call some other open source model that is called diffusion model to generate this image. And this is very controversial, and the company's reputation is also damaged. Later, the company released a statement saying that, okay, we indeed we reuse the diffusion model, but we change it, we redevelop it. Now it's different from the original diffusion model, but it's our model. It's still very controversial. I mean, I'm not going to check the fact of this. And there are also other stories, like in the news, OpenAI claimed Google use ChatGPT interface to train their model, and Google refused it. The thing is, there are many such similar news. But the thing is, nowadays, I mean, almost all companies who are developing large language models, we could reasonably assume that they will not develop the large language model from scratch. They will more or less use ChatGPT in some form. And this brings a very interesting question. So how can a company prove a model is your model? Your model is your model. How to prove that? What evidence is needed to prove that your model is your model instead of diffusion model or ChatGPT model or other models? What are the evidence needed? So that is the main motivation of this work. We are going to, I mean, by seeing artificial intelligence in this talk, by default, we assume it's something called deep neural networks. For those who are not familiar with deep neural networks, so this is a deep neural network. So it has some input, it could be fancy images. It has some output that could be the label of this image, text. And deep neural network has multiple layers. Each layer comprises many neurons, and the computation is propagated from layer to layer, from neurons to neurons, until you get the output and get the label of the model. So I mean, this is the deep neural network model. And suppose that you have a deep neural network model. There are a few ways that other people may change your model for their purpose. There are a few common ways. The first one is something called model fine-tuning. For example, yeah, it works. You see, it works. So model fine-tuning, for example, the attacker or the other people, they may fine-tune the parameters of the last layer of neurons, so that, I mean, they fine-tune your model for their purpose. This is very common. I mean, many people use this model fine-tuning for good purposes. Ah, sorry. I know. Yeah. No worries. My fault. Okay. Another popular way is called model pruning. For complex neural networks, there are millions of parameters, more than millions of parameters. Parameters meaning that these connections or the weights of the neurons connections and so on. And the thing is, most of them are redundant. That's true. I mean, most of them are redundant. There are millions of parameters. If you reduce 60% of them, I mean, your model's performance may or may not change that much. So that is called model pruning. That is, you prune out some neurons, some connections from the model to fit your own purpose. I mean, these are all very common approaches for another simple approach to change somebody's original model for their own purpose. And the evilest and the most powerful one is something called model extraction or model stealing. That is, I mean, only by querying the input and output of your model, so people could extract a copy of your model, people could create a similar model that is similar, has similar performance than original one, than your original one. I mean, this is also the original example I showed you that okay, by only in the first slide, so that by only querying input and output, so the public API of the big models, people could recreate a similar model with much less effort and budget. And I mean, the model stealing, I mean, it poses a very big challenge for protecting any machine learning models. I mean, how could you prevent from people replicating or extracting or stealing your machine learning models if they could do so by only querying the input and output? I mean, you have to, the developer, the business, they must provide the service to the user. And as long as you release the API for input and output, so I mean, attackers could already steal your model by using such interfaces. There are some defense works to prevent people from stealing your model. For example, you could add some mask on the input, or you could also encrypt the input or mask the output. But the thing is, typically, such defense techniques, okay, they may prevent people from effectively steal your model, but it also compromises, sacrifices the original performance of the machine learning model. So fundamentally, I mean, I don't know. I mean, this is not something concluded, but fundamentally, I believe you cannot, I mean, under certain assumptions or without certain assumptions, you cannot prevent people from copying your model or stealing your model. I mean, this is my impression. I haven't proved that, but I mean, you can agree or not agree. And the next thing is, I mean, if we cannot prevent, or it's very hard for us to prevent people from making a copy of my model, so can we identify when people does so? So that is the technical route you are going to see in this presentation. And in general, I mean, our work fits into the problem of who owns AI, that is, who are the owners of AI. And this problem could be really sophisticated and general. And I mean, as a computer scientist, I cannot answer this big question by myself. It must involve academics, big companies, and also policymakers. And in this talk, in the next part of this talk, so I will focus on a more technical sub-question of this general question. That is, you have a model. Somebody makes a copy of this model using one of these techniques, makes a copy of your model using these techniques. So can we identify such a copy? So for the next, I mean, we are going to switch to a more technical focused tone of this. Fundamentally, I mean, this problem of identifying the copy of your original model, fundamentally, it's something called the model equivalence check. That is, you have two deep learning models. Can you prove that they are equivalent? Equivalence meaning that they are not only working correctly at the same time, they are also working wrongly at the same time. So there is a fundamental research problem for model equivalence check. And of course, this is very complex work, and there are some proving works such that they could prove that, okay, model A is equivalent to model B. The thing is, I mean, such work is also subject to limitations of scalability. In theory, they can check, but in reality, they can check the equivalence of models of very small size. So in reality, I mean, we are talking about models of millions, if not billions of parameters. Watermarking is one of the first approaches that was used by machine learning researchers to protect the IP, to claim the IP to their machine learning models. So we just, I mean, if we look at the example we just saw for dog and cat recognition, I mean, for your own cat, you can put a watermark like Luna. Luna is, I checked, is a good name for cat. So you can put this Luna watermark for your own cat, such that you train your model, when you develop your model, you train it to recognize this watermark Luna. And if another model also identifies this watermark Luna, then you have strong evidence saying that, okay, the other model must be somewhat related to your model, rather than independently trained. Fingerprinting. So we humans, we have fingerprints that are unique to each body. And there is good hope that machine learning models also have their own fingerprints. Yes or no, but people are making efforts on this direction. So for example, in our dog and cat classification problem, okay, there are many so-called decision boundaries that such that in the input space to distinguish between dog and cat. And the thing is, okay, for your own model, you identify some decision boundaries. If the other model, they have very similar decision boundaries as your model. So, okay, the other model is very likely to be related or dependent on your model. The thing is, I mean, the exact characterization of decision boundary, I mean, it's another very difficult and fancy problem, but people use approximation techniques to do this. And there is also so-called adversarial decision boundary. I mean, adversarial input is a kind of particular input that people crafted for misleading machine learning models. So you can also use it, apply it for characterize the fingerprinting of machine learning models. And ourselves, we propose some approach based on software testing. So if you are familiar with the software testing, when you test the software, it often involves 2 steps. Step 1, you need to define some metrics for helping you decide, okay, how good or how bad, how adequate the testing of your software is. And then you generate test cases for exercising these metrics. And we apply this idea to identifying the copy of machine learning models. So how to do this? I mean, we propose we define a few metrics for characterizing the distance, the similarity between 2 different machine learning models, similarly to the metrics for testing software. So the first metric is something called robustness property. So it's based on the input. So it's very similar to the idea of fingerprinting. So basically, I mean, in principle, it's the same as the fingerprinting idea. So you have the decision boundaries, and you use these decision boundaries to quantify the distance, the similarity between 2 machine learning models. The closer they are, the more similar the 2 models are. And we also open, I mean, I just very briefly introduced you what a neural network is. If we are glad to open the neural network a bit, we see that, okay, there are many neurons. And if we look at each particular neuron of this neural network, and if we give some inputs to it, I mean, you will see that, okay, each neural network neuron, it has some activation value. And its activation value, I mean, it follows some distribution. So there are some values, activation values of the neuron after the computation propagated. So they are more often triggered. There are also some rarely triggered activations for your neurons. So the idea of this neuron level metrics are that, okay, given your own neural network, there are some neurons, and you have the test set. By running the test sets, test inputs through the neural network, you observe that, okay, for the selected neurons, some rare corner activation values are triggered. So they are rare. If you give the same test inputs to another model, if the same very rare corner values are also triggered, I mean, if such evidence is accumulated for many neurons, for many test cases, then you build some connection between the two machine learning models such that they are less likely to be independent from each other, but one must be derived from another. So this is for each neuron of your neural network. I mean, a neural network has so many neurons, and all the neurons are each neuron is associated with some layer. So we could generalize this neuron level distance to layer wise. So for each layer, it's a vector or metric of activation values, and you can also define the distance between two different machine learning models by using layer-wise activation patterns of your neural network. And these are the metrics we define. We want to use these metrics. Each of them will tell you, okay, what's the distance, what's the similarity between two machine learning models from one characteristic from one direction. And then we generate the test inputs to exercise this matrix. By the end, I mean, each of these metrics will tell you a number. So this number indicates if these models are close or if they are far away from each other. So each of them will give you a number. And by the end, okay, you can use a majority vote to decide if the two models are close or are independent. I have to admit that in our original design, so we are pretty happy about this number from each metric because we believe that they are evidence. They are evidence that we hope that we could show in the court. So if there is some dispute between the ownership of the machine learning models, so we hope that this could be the evidence to show to the judge. Okay, you see, and how close according to this metric, that metric, and so on. And indeed, I mean, I tried to talk with some lawyers. And I mean, the advice is no, do not show me this number. Show me the decision. Show us the decision, not this number. So this is why there is this majority vote. That is, okay, we have this metric number, and then we have this majority vote to decide yes or no, if it is a copy or not, if it is not a copy. And because it's our own work, so we also developed some open source tool that people could use and play with their own examples. So this is the summary. Really, I mean, this is not about which work, which technique is the best. Really, it's about what are the challenges, what are the problems are. For example, I mean, watermarking is the most popular approach. I mean, its idea, its motivation is from multimedia copyright protection, very natural. However, similarly to multimedia copyright or watermarking, so such watermarking could be washed out, could be erased. But the thing is, if you want to put a signature to your machine learning model, so watermarking is still the most useful way. And fingerprinting has been studied quite often by machine learning researchers. And as I just told you, I mean, fingerprinting could be used in our testing framework, as a metric. And our testing framework, I mean, we believe that its biggest advantage is it's extensible and adaptive. So it could be adaptive, it could be expanded for new defense and attack techniques. This is very important as well. We need to see some evaluation results. So evaluation, in the evaluation, okay, we have some data sets. The most interesting one will be the ImageNet. The ImageNet data set is something called high resolution imaging. So it's for showing that okay, our approach or the approach could work on most complex models on the most complex data. So ImageNet will be the most interesting one. And we train some model. So let me tell you about this positive and negative means. You see this red color, right? Red color meaning dangerous, vulnerable. Once my students show me a table of all red color cells and tell me that they are all completed, so they are all red color, I told him change it to green color. Anyway, so we have the original model. Then we train two groups of models. For the positive suspect model, so they are derived from the original model in the sense that okay, they are fine-tuned from the original model by fine-tuning all layers, or retrained from the original model by retraining all layers, or retraining last layer. All they are ruined from your original model, ruin certain percent of the parameters of your original model. And also there is model speeding, model extraction. That is, you have your original model, and this group of positive models, they are derived from your model one way or another, and they should be copy of your original model. In the meanwhile, the negative suspect models are independently trained. So they are independent from your original model. And the most interesting thing we are going to see is can we distinguish positive models from negative models? So yeah, it's very interesting. So these are the results on ImageNet. Let me explain you. First of all, I mean this is fine-tuning. This is okay. We use the metric. These are the metrics. So each of this direction is the metric we just saw in the table, and this is the positive suspect model by fine-tuning all layers. Positive suspect model by retraining all layers. Positive model by pruning certain percentage of the layers. And on the other hand, we have the negative model independently trained. The first good thing is, I mean, they look very different, right? They look very different. So what does it mean? It means that, okay, so let's say for fine-tuning for this positive suspect model by fine-tuning all layers. So we measure its similarity, its distance with the original model in multiple dimensions defined by the metric. And for each metric, I told you they return a value, they return a number, and we normalize this number. The idea is the closer this value, the closer it is to number one. So the more similar this model is with respect to the original model. And in this sense, we could see that for negative models and for positive models, so they have a very different shape. And yeah, I mean, so we answer the first question. First, we can distinguish between positive models and negative models. And the greater, the bigger this area is, the more similar this model is to the original model. So positive models, negative models, they can be classified, they can be distinguished. If we look at the pruning, the positive model by pruning 20% of your original parameters, and the pruned model by pruning 60% of the original models. I told you that the larger this area is, the closer this model is to the original model. I mean, understandable. I mean, by pruning 20% of the original model's parameters, naturally it results in a model that is more similar to the original model by pruning 60% of the parameters. And if we look at fine-tuning, I mean, by its name, fine-tune and retrain. So by its name, naturally, I mean, fine-tune meaning making less modification, less changes, and as a result, by making less changes, the resulting model is closer to the original one compared with retraining. So I mean, this covers the first two kinds of threads we saw in the first slide. That is fine-tuning your models and pruning your models. Okay, if somebody fine-tune your model or prune your model, we can rather relatively easy to identify them. I mean, this is not that difficult. We can relatively straightforward identify them. The most challenging part comes from model extraction. I mean, do not read this table. I mean, there's no need to read the complete table. But the idea is that as we saw earlier, so model extraction, it only requires input, output queries, and it will replicate your model. So in this case, we have three positive models that are extracted by three model steering techniques: GBA, NOC, and ESA. And we have negative models that are independently trained as well. And if we look at the results, so this is the majority voting result. We have two metrics defined because it only relies on querying input and output. So we cannot open the box of machine learning models. We can only rely on the input output for defining the metric. So this is why only two metrics are used, and we have this majority vote. And according to the majority vote, okay, for the positive models by GBA, unfortunately, the majority vote does not identify that it's a positive copy. But for the other two, knockoff and ESA approach, okay, they identify that okay, they are indeed derived from your original model. And for the independently trained model, the majority vote also successfully identify that they are negative suspect models independently from your original model. So the most interesting part would be this GBA approach. GBA approach to steal your model, to extract your model. Why does it bypass our identification? Why our identification fails to recognize that this GBA approach extracted model is derived from your original model? So let's look at some numbers. If we look into the details, we will see that okay, there are two data sets. One is MNIST, one is CEPA10. And for the MNIST one, so the GBA approach, okay, it extracts a model from your original model. And the extracted model's accuracy is something around 84%. The original model's accuracy, I can tell you, it's more than 99%. This gives you some hint, right? And on the other hand, for this CEPA10 model, we can see from here. So for the knockoff approach, it extracts a model from your model with accuracy almost 95%, because we run multiple experiments. So there are some standard. And also for ESA approach, so it's also 89%, much higher than 84% GBA approach. If we look at the CEPA10, it's the same. By using GBA approach, so the extracted model's accuracy is around 40%, and for the other two, their results are 75 and 67%. So you may already notice that. That is, although our detection approach did not identify that the GBA extracted model, we do not regard it as a copy of the original model. It's largely due to the fact that the extracted model by GBA is rather low. This is rather low. I mean, for MNIST, I mean, normally expect something higher than 90%. And for CEPA10, I mean, 40% is also very low. So this is really very interesting observation we see, because if we assume the attacker also faces a dilemma here. The dilemma is, okay, if the attacker would like to steal your model very accurately, if the attacker would like to steal the 100 performance of your model, so it's easier to identify. It's easier to identify if you, especially if you want to put into the numbers, but we are not going to do it anymore. On the other hand, okay, the attacker may bypass your defense, bypass the identification by extracting, by stealing a not so well performed model. So okay, we are not going to identify. But the thing is that model will also not be very useful. So the attacker also face a dilemma here. Whether or not to steal a very powerful model that can be easily detected as a copy, or steal a less useful model that cannot be detected. I mean, there is always a dilemma in life. Huh? So this is for model extraction. We are pretty happy about this observation. The story does not end. The story does not end. And attackers, I mean, I learned a lot from Danny. I mean, also Danny and myself, we teach some security course, and we have many amazing guest lectures. I also learned a lot from them. And one thing we should remember is the attackers. I mean, they are very smart. They are very smart. And they will also, I mean, you have defense techniques. I mean, attackers will be aware of that. I mean, when good attackers, before they do attack, I mean, they will also try out defense techniques, defense tools. And that brings something that is called adaptive attack and adaptive defense. So, okay, we have our defense testing-based or other approach-based approaches to defense, and the attacker is also aware of that. I mean, what if the attacker knows our defense technique and they also practice it by themselves? And can we, or this time, I mean, can we identify this copyright violation? So that is something called adaptive attack. Again, do not read this table. The important thing is, okay, we design some adaptive attack techniques, and I mean, by assuming that the attacker knows our metrics, the attacker knows our test cases, so different assumptions. And as you can see that, okay, I mean, if you look at this majority vote, yeah, because it's our table, so we show the best results. Can we cut this sentence out? I don't know. I mean, that's fine. In general, it's effective. But as you can see that although the majority vote can still identify such stolen models subject to adaptive attack, but it became more difficult. I mean, if you look at the previous tables, I mean, the majority vote is all agree, all disagree. But now you see disagreements. Luckily, we have the majority vote, so we get the right conclusion. But the thing is, okay, if we assume that the attacker knows the defense and they can also update their attack, we definitely face greater challenges. And this is, I mean, we should be confident that the attacker will be developing more and more sophisticated attack techniques. They will also integrate our effective defense techniques. But the thing is, the best thing they can do is also to extend our defense techniques. So this is called adaptive attack and adaptive defense. A good thing about the testing framework is that there is new attack. Okay, we may design new metrics to cover it. Actually, we presented our work in S&P Outline conference, and in that conference, there is an audience sitting there and asked, okay, we proposed a new attack. Can you defend it? No, we cannot defend it. But next day, I mean, we submitted a journal extension by expanding our framework to defend this new attack. So there is an endless attack and defense game. I mean, that's the interesting part, I would say. So I mean, a lot of open opportunities and open challenges. I mean, this talk we focused on, for example, the model protection of the machine learning models, and but on the other hand, I would say data may be something also very, very interesting. So instead of making a decision, okay, whether or not your model is derived from some model, can you make a decision whether or not your model is derived from some data? Can you do that? Data is, I mean, there are many concerns on the security and privacy of the data, right? So there are also other challenges. Actually, I did a small test, ad hoc test to ChatGPT. I asked the ChatGPT, I give it a Wikipedia page, and I asked the ChatGPT, is this page part of your training data? And the ChatGPT seems to be very honest, and it says that yes, it is. It was used in its training data. However, the thing is, by the end of the day, to what extent, I mean, we are going to trust the answer from ChatGPT. So that's all from me for today. Thank you very much. Thank you.
So I hope you all learned a lot from this talk, and it's your chance to ask a few questions to the very speaker. So who's first?
So if the data are public, so we don't own the data and we create a model and the other person takes the data because you're public and they create another model that is similar to ours, then we cannot say something to the other person, right? Because the data.
That is exactly how we train the independent model or the negative model. That is, I mean, we use the same training data and we train two different models. Actually, they are different. They are different. I mean, you can see from the results the spider net. So even by using the same data, you can still identify the difference between two independently trained models from the same data.
And my other question is, can someone steal a model but split it in smaller models? So we cannot identify their native. So if you want to predict a line, maybe create two models, one predicting the offset with the other. So how you can prove that?
Yeah, I mean, this is exactly. I mean, I haven't thought this before, but this is exactly what I said. I mean, the attackers are very talented and very smart, so it could happen, but I don't know. I mean, I never saw such cases. I haven't seen such cases. This might be related to something. I mean, this might be more related to something called federated learning, because you have the local agents, you have the final model, but I haven't seen particular attack on it. But it sounds, it sounds very dangerous to me.
Next question, I think is Danny.
Yeah, because this is a kind of a question about the stage before. All very worried about thieves stealing the model, but also I think there's a case just starting of people suing Google or ChatGPT or whatever about the inclusion of their texts and the like, in those models. Mm-hmm. Are there reliable tests to prove that this model was trained on that data and therefore lead it to the ownership of the original copyright?
I mean, this is another very active and very relevant direction. I mean, the two. I mean, this is exactly why I raised this question to ChatGPT, and this is very active topic as well. And I would not pretend that there are many solutions. But I would not pretend that there is one universal functioning solution that could be ideal. I mean, there's still a large space for more engagement and more works on this direction. And one challenge here is, I mean, I hate to say that, but it's true. I mean, even my talk, I mean, it's still very, I mean, computer science oriented. I mean, very technical oriented. However, the thing is, I mean, computer science is ourselves. We cannot answer the fundamental question. We can provide some technical support, some technical evidence, but actually we cannot. I mean, the question, Danny, you raised, and also this one we just I presented. I mean, the thing is, it's so complicated. I mean, a pure technical solution is meaningless without proper justification or interpretation by domain experts. That's my I sincerely feel the limitation from a technical guy's perspective.
Just looking at that there, could ChatGPT think, actually be wrong, that it wasn't trained, it just saw so many other references referencing the original text that it thinks it's seen the original text. Is it protected against that? So it knows, what patient zero was for the training?
I mean, ChatGPT, of course, it's often wrong, right? It's often wrong. But the most correct answer is we don't know. Because nobody knows about this. I mean, the other day I saw a job advertisement from OpenAI. They are hiring some people to reverse engineer ChatGPT. Yeah, so I mean, nobody. I mean, it's very difficult. I mean, it's supposed that. I mean, we cannot prove it's always correct or always or it is not wrong. I mean, my impression is, personally speaking, I believe that. I mean, we cannot 100% trust the answer from ChatGPT or other large language models. But we don't know. I mean, honestly, we don't know. Nobody knows. I guess that's the problem of understanding. Thanks.
Okay. So we have a question from the back. Yeah.
Hi, so thank you for the presentation. I'm from the law department and I actually research AI and copyright a little bit, but the technical part is really new to me. And yeah, as you say, this topic is sometimes overlooked by us as well, legal researchers, because basically we're divided into two camps when we look at AI and copyright. It's either the input data and text and data mining defense can be use someone else's data for tuning, or the output, the original enough that it deserves copyright protection. The kind of deep learning models, they do come up, but they're usually almost like an afterthought in between these two camps of discussions. I belong more to the first group of input data. But when it comes to machine learning models, I mean, my instinct is basically, in order for us lawyers to discuss it, we need to first figure out if they're protectable by copyright, which would require comparing them to computer software and the existing case law. And then how much of it's copied, how much of it is copied, again, required on computer software. And overall, it's also difficult for us. So when I was a postdoc on this similar topic, then we had joint meetings with computer scientists. We just see things very differently. So overall, not really a question, but I think events like this are really helpful because we just see things differently and we just focus more on the ownership based on what goes in or what comes out. The inside of it is the mystery still to more things. But there is some research going on in this.
I mean, so thank you so much for your comment. I mean, this is exactly what I hope best for this seminar. I mean, I wanted to exchange ideas with different people, and especially from people with some backgrounds of years. But exactly, I mean, regarding we initialized, I mean, our work without talking with non-computer scientists. So I think that is our limitation. I mean, and we wasted so much. I mean, I had to say that if we had another chance, I mean, before we start this work, I want to talk with you. I want to talk with people from the other hand of the research, the other side of the research. I mean, that will save us a lot of things. Yes.
So I'd like to ask maybe a technical question.
Yes, sir.
So in your approach, you used so 6 metrics to measure the similarity between models, and in conclusion, you said the conclusion is made by the majority of both.
Yeah.
So my question is, why do you choose this particular method to make your conclusion?
Yes. I mean, so let's go back to the vote. I mean, first of all, I would say that originally we thought that these numbers are very good, but we had some feedback from people with more background. And more importantly, I mean, the reviewer asked us, okay, you should have a binary decision instead of multiple one. And actually what we did is we could I mean, this majority vote, we have each metric, it gives you yes or no, or far. So we need to summarize them, how to summarize them. So we developed some baseline models, and baseline models, and we measure some baseline numbers for this matrix, and then we apply it so about this baseline, below this baseline, so they have this majority vote. But I would say that I wouldn't say that this is this is 100 correct also. I mean, our approach is indeed very naive. Suppose that you have 60 metrics, 100 metrics, what are you going to do? We were even thinking about training another machine learning model to identify this. So I mean, this is just a very, I would say it's not it's not complex at all. I mean, there is a space for making things better.
And so, like for each metric, it's a binary answer. Again, so it's your score against the threshold,
yeah,
which gives a binary results for each metric.
Yeah.
All right. Yeah, because the slide says like I thought it was a scoring system based on the slide. Yeah. So, probably.
I should make it more clear.
Yeah. Also, another question is could you go to the slide with your results?
Yes. Which one?
Yeah, this one. So I'd like to focus a bit more on your results of the JPA methods.
Yes.
So I understand you said that the hackers are facing a dilemma, but from maybe the owner of the model's perspective, this particular method maybe failed. Your approach maybe failed to detect this method, this particular model. But from the owner's perspective, should they worry about this model with lower accuracy?
I mean, from the owner's perspective, that means the owner should train the model as accurate as possible. So in that way, I mean, if the attacker would like to steal the performance of this model, so they need they will face this dilemma. I mean, if the owner's model is already bad, so we cannot distinguish them as you saw here. So the owner, I mean, there's no restriction on the owner. The owner of the model should try their best to develop a good model.
All right. Thank you.
Thank you.
Okay, so I think we have time for at least one more, right? Maybe let's do.
More of an observation. Thank you for that talk. That was really helpful. I'm an intellectual property solicitor, and we're getting absolutely inundated at the moment with queries from clients on AI. We're trying to apply really old legislation to new kind of concepts. And I think one observation that I have listening to this is just that it actually seems quite scientific in terms of I can see that there would be disputes around what model to use and what metrics to use, but then the outcome, that seems like it would be really difficult to actually argue when you've got something there that says, you know, we compared it all and it is actually a copy of what it isn't.
Yeah, I mean, I agree. So as I just mentioned, I mean, we started this work without talking with the IT people, without talking with the lawyers, and we are very happy. We were very happy about this work. This is great work, and also other computer scientists. Oh, this is a great idea. How could you come up with such an innovative idea? The thing is, then I talked with people. I talked with people with no background, but still, I mean, in the limited scale, and each time, I mean, I cannot explain, I cannot convince them. That is my, I admit that. I mean, I cannot convince them that this is the thing that you have to use. This is the problem that you have to address. I mean, to some extent, I felt a bit down. But the good thing is, each time I talk with more people, with people from different backgrounds, I mean, I learn something. For example, they give me some advice, I learn something. And I mean, this work is not the conclusion of the research. I mean, it's really one small piece of this big research problem. And I mean, I hope that next time, if we can work on a similar problem. I mean, there could be the involvement of people from different interdisciplinary, so that I mean they start from the beginning. I mean, from the beginning they start from something that people from different backgrounds they all agree. This work, I mean, technically speaking, I mean, I'm still very proud of it, but I have to admit that I also feel the limitations and the difficulties to sell it to the end user, that are the lawyers and the legal people. So, but I hope it's something useful for future work.
No, Glenn, well, thank you. It's just, so I specialize in disputes, and I was just thinking, if I was in a court and trying to argue that something was already an infringement, but then there were these figures in front of me that said, you know, they've done an expert done the analysis and said it is a copyright, it isn't. I think it would be really hard to move away from that.
I think by this work, I mean, I learned, I mean, as a technical guy, I mean, really from this work, I learned that as a technical guy, we should be humble. We should be really, really humble, because, I mean, sometimes we believe that techniques are powerful, it could solve all the problems, but no. I mean, techniques could be useful for helping people to solve the problem. And that's something I learned from this work. Yeah.
Okay, one more quick question.
A follow-up question. I'm like your turn, actually, so there you go. It's like to mention my sister, but it's a follow-on question to the ladies, actually. Could this be used to actually prove that the original copy has copyright in itself? And I think that's what your lady Cindy was hinting at earlier, was to infringe someone's copyright, there has to be copyright protection of the original model. So how do you prove the original model has its own new and original over what is gone before, so that it has copyright protection and therefore that has been infringed? So you have to go back one step before this can be applied in a court of law to prove that there was copyright and then the copyright has been infringed. Do you see what I'm saying? So is that something that you might think about is actually how do you prove that the model that has been copied has copyright?
I haven't thought about it.
Yeah.
So
do you understand?
yes, I mean, thank you so much for your comment.
Yeah.
I haven't thought about it. But I mean, maybe I can.
That's what you see, that you actually have to prove the model has copyright first before you can prove infringement.
I think that's a recursive problem as well, right? Because you don't have to go into the model for that potentially that previous model.
There is one thing maybe I can ask. So, something I did not mention in this talk is there are each year there are, I mean, companies or major countries, they invest a lot of money on patenting the AI algorithms, AI models. But I mean, this is my observation. So there is a patent law between major stakeholders for AI algorithms or AI models. But I don't know how to interpret them. I don't know if this is related to your question about the copyright, the copyright eligibility of the original model. Or I mean, I will not. I mean, I will not try to interpret that because it's not.
Yeah, I mean, if you can patent it to test this whether it's new and invented from before, but copyright is a different test. It has to be original. Over what's gone before. So it's interesting. I just, yeah, I mean, it is a recursive problem.
Okay, so I can interfere in that and just announce that we have about half an hour of time scheduled for networking. So you just have more discussions. I think the second you can go into the science. I think Youcheng will appreciate it a lot. We can take even a more offline session. So thank you all for coming.